Bismillahirrahmanirrahim. In this lecture we will discuss orthogonal tensor and transformation matrix between two rectangular Cartesian coordinate systems. Orthogonal tensor. Let us define an orthogonal tensor. This is like the definition of the orthogonal matrix. What is the definition of orthogonal matrix? This is written here: Q transpose. If Q is matrix, and if Q transpose Q is equal to identity, or Q and Q transpose is equal to identity, and Q transpose Q is equal to identity, then we will say that Q is orthogonal. So let's see how we will derive this definition from the definition of the orthogonal tensor. An orthogonal tensor is a linear transformation. So it is basically a linear transformation. For tensor, it must be a linear transformation. So it is a linear transformation under which the transformed vectors preserve their lengths and angles. Now this is the definition of the orthogonal tensor, that under this transformed vectors preserve their lengths and angles. Now what does this mean? That if A and B are two vectors, then the transformed vectors are QA and QB. No, by this definition, if Q is orthogonal, then by this definition, for any A, B vectors, the transform vectors QA and QB, according to the definition, length of QA will be equal to length of A, and length of QB equals to length of B, mod length. This is the first part of the definition, that their angle must be preserved, that before and after transformation, their length must be preserved. Before and after transformation, length will remain same. If A and B are vectors before transformation, and after transformation we have QA and QB, length of QA will be equal to A, length of A, and length of QB will be equal to length of B if Q is orthogonal. This is the definition. And if any vector follow this definition, this is first part. And then second part is the angle. They will preserve the angle, that is angle cosine of AB equals to cosine of QA and QB. Cosine of angle between AB will be equal to cosine of angle between QA and QB. QA is after transformation and QB is also after transformation. The angle must be remain same. Cosine of AB equals to cosine of QA QB for any AB. So this is what does this definition mean, that if Q is orthogonal, then Q is equal to A, QB is equal to B, and cosine of AB equal to cosine of QA and cosine of QA and QB. So this is from the definition. Now, by using this definition, we can have this relation QA dot QB equals to A dot B. How this will come? This is very simple. QA dot QB. These are two vectors. QA and QB. These are two vectors. These are the transformed vectors of A and B. So apply the definition of dot product on these two vectors. QA dot QB will be equal to mod of QA mod of QB and cosine of angle QA and QB. As we know that Q is orthogonal, so length of mod of QA will be equal to mod of A, mod of QB equal to mod of B, and cosine of QA QB will be equal to cosine of AB. So it means that in second step we have mod of A, mod of B, and cosine of AB. This will be equal to A dot B simply. A dot B equals to A mod B mod cosine of angle A and B for any AB. So this is coming from the definition, that if Q is orthogonal, then QA dot QB will be equal to A dot B. Now we will use the definition of orthogonality, and we will reach at the usual definition of orthogonality. No, using the definition of the transpose and the product of tensors, we can write qa dot qb equals to, this is the definition of transpose, that we are considering qa as one vector and q is transformation and b is another vector. Then by definition we can write b dot q transpose of qa. Similarly, a dot tb is equal to b dot transpose of t act on a. Now here we have used product of tensors, that s and t, s of ta equal to st whole a. Here we are using, here we have used transpose, definition of transpose, and here we have used product of tensors, definition of product of two tensors. Now we have written this side, this side on here, b dot q transpose qa. Now how this is equal to a dot b? Because we know that b dot q transpose qa equals to this qa dot qb, and this is equal to a dot b. Here it is written. So it means that this is equal to this a dot b. So we can write b dot q transpose q equals to a dot b, and this can be written as b dot a, and this also can be written as b dot ia, identity transformation. A equals to ia if I is identity, if we are using I as an identity transformation. So this can be written as b dot a equals to b dot ia. So this will be, this can be written as, this is for any arbitrary a and b, so it can be written as q transpose q equals to this identity. Though this is the used definition of orthogonality of matrix, orthogonality of matrix q. So it means that inverse and q transpose are equal. So from here, this equation, we can write this thing, q transpose q equals to q transpose identity. Now in matrix form we can write this as, q transpose equal to q transpose q is equal to identity matrix. Now in subscript notations we can write this thing in this way, that is this qim qjm equals to qmi qmj, and this we know that subscript notation for this is delta ij. Now this is the equation 2b 10.2c. you will have to derive this equation. So do not write directly from here to here. There are 2 to 3 steps to reach here. So use your previous lectures and write this thing and derive this equation. So it's up to you how you will do that. Now these are the examples. Now in this example, let's see what happens. The tensor given in example being a reflection is obviously orthogonal tensor. These are the examples of orthogonal tensor. That the tensor, reflection tensor, in the previous examples we have seen that. So we will have to verify that how it is an orthogonal tensor. Now T, this is the reflection, this is the tensor corresponding to reflection of plane yz. This is the transpose, multiply these and we have this identity. Similarly, if you can write this tt transpose transpose tt, I mean this equation, this t q transpose q equals to q transpose q is equal to identity. So it means that this is an orthogonal tensor. So if we will go for its determinant, no, this is another result which we are going to write for orthogonal tensor. If you will go for its determinant, then we will have its determinant -1. Now there is another example which is related with the rotation. In this example, we are seeing that this tensor is also orthogonal tensor. Let's see how it is an orthogonal tensor. We have calculated this. You have to also calculate R transpose R, that must be identity. So let's calculate it. So it is orthogonal. Identity, so R is orthogonal. Now this is example. This is the example. This example is about the rotation matrix R, which is given in this example. Now let's see its determinant. This determinant is +1. So determinant of the matrix of any orthogonal tensor Q is easily shown to be equal to +1 or -1. No, here we are checking that its determinant is +1 or -1. That if Q is orthogonal, then its determinant +1 or -1. Now, we know that this is equal to identity. Let's take determinant on both sides. Left hand side of this, we can write this as, and on right hand side this is identity. We know that identity is 1, and determinant of Q and its transpose is same. So we can write this as whole square equals to, this is +1, determinant of identity is 1. So this can be written as +-1. So it means that if Q is orthogonal, then its determinant is either +1 or -1. From the previous example, we can see that if it is +1, that it means that we have rotation. Orthogonal matrix is a rotation matrix, and if it is -1, then it means that this matrix is coming from the reflection. Now we will go for the transformation matrix between two Cartesian coordinate system. That we have two Cartesian coordinate system, and we will go for the transformation matrix. With the help of that, we can go from one system to another Cartesian coordinate system, and we will see that this matrix must be orthogonal. Suppose we have set of two unit vectors EI and EI dash corresponding to two Cartesian coordinate systems. So one is prime coordinate system and other will be unprimed coordinate system. So this is seen in this figure here. E1, E2 and E3, other is E1 dash, E2 dash and E3 dash. These are the unit vectors for the primed and unprimed coordinate system. Now we have to go from one system to another system. So it means that we need a relation between the base vectors of two systems. It is clear that we can make the EI to EI dash with the help of a rotation or reflection, either rotation or reflection. That we can make EI to coincide with EI dash through either a rigid body rotation if both bases are same-handed, or a rotation followed by a reflection. In previous two examples in which we have talked about the reflection and rotation, we have seen that we are relating the bases of we are relating two bases EI and EI dash. So with the help of, if your bases are same-handed, if both the bases are same-handed, then it means that we can relate both bases with the help of rotation, and if they are different-handed, then they can be related with the help of rotation followed by a reflection. No, what does same-handed mean? Same-handed means if both are right-handed or left-handed rotations, and if they are if they are different means that if one is right-handed or and other is right-handed. Now, what is left-handed and right-handed mean? Right-handed means that you have counterclockwise, that you have x-axis along horizontal, y-axis vertical, and for left-handed means that x-axis, y-axis vertical in upward direction, and if it is counterclockwise then it means that if it is clockwise it means that we are talking about left-handed, and for left-handed x-axis along along horizontal axis, and second y-axis is downward, perpendicular but downward. So this is left-handed, and it means clockwise, right-handed, counterclockwise. And we have seen that matrix which is related with rotation and reflection. In both cases, that matrix is orthogonal matrix. Now we will write this equation 2b11.1a, that which we are relating both the bases, that Q is acting on EI and giving us EI dash. EI base vector, when Q acts, orthogonal tensor acts on that EI, it will give us EI dash basis of second system, and this can be written as QMI with the help of your TEI. There we have T and here we have Q. So you need to think that how can we relate EI and EI dash with rotation if both are same manner. This is easy thing. And if EI and EI dash are different handed, then first rotation, then reflection, then you have the relation. So you will have to think about this. Now EI dash equals to QEI equals to QMI. This is the relation between EI and EI dash with the help of tensor Q. Now this is E1 dash. Simply you are giving the value of I1, 2, 3 and opening the summation on M. This is E1 dash, this is E2 dash, this is E3 dash. But as Q is orthogonal, so this can be written as we are using from the previous thing. Or QQ transpose equal to Q transpose Q is equal to identity. Now if we want to calculate this Q11, this is a similar. Q11, we will have to take the dot product with E1. So this would be E1 dot QE1, and the right hand side will be equal to E1 dot E1 dash. Here it is, QE1 dot E1 will be equal to E1 dot E1 dash, and this is equal simply cosine of angle between E1 and E1 dash. This is dot product, and you can open this mod of E1 dash and cosine of angle between E1 and E1 dash. length of E1 and E1 dash is 1 because they are basis vector unit length. So Q11 is cosine of angle between E1 E1 dash. Q12 is cosine of angle between E1 and E2 dash. Similarly, we can write it as Qij equals to cosine of angle between Ei and Ei dash, and this can be written in this way, that Qij equals to cosine of angle between Ei and Ej dash, and this is simply this Ei dot Ej dash. No, this is the matrix, simply Qn, and called these are the directional cosines, matrix of directional cosines, Q11, Q12, Q13, that Q11, Q21. From first we have first column, second column, and from E3 dash we have third column. This is the matrix Q which relates both bases. Now this is the example that if you have Ei dash, the prime bases can be obtained by rotating Ei about E3 axis, that we have fixed x3 axis through an angle 30 as shown in the figure. Let's see figure. This is E1, this is E2, and your third axis is fixed, that we have rotated. We are rotating the system about x3 axis and obtaining the dash system, E1 dash and E2 dash, with an angle 30. This is 30 and this is 30. We have to calculate the orthogonal matrix Q, transformation matrix between two systems. Simply you need to calculate 9 components. Q11. What is Q11? Cosine of E1 dash, and between E1 and E1 dash we have 30, so cosine 30 is this. Q12 cosine of angle between E1 and E2 dash. You can see E1 and E2 dash. This is cosine of angle between E1 and E2 dash. This is 30 plus 90 plus 30, 120. And this is Q13, cosine of angle between E1 and E3 dash. This is Q13. Similarly, you will calculate all these angles, all these components, and then you will write Q. Now here it is easy to simply look at the figure 2.2b. This is second way. Also with the help of this, you can use directly the relation. This from this, you can take this from your previous example. Which one? You can take this, you can take that matrix Q from the example 2b 2.3, in which you can see that E1 dash, which is RE1, will be equal to cosine theta E1 plus sine theta E2, and here is E2 dash minus sine theta E1 and plus cosine theta E2. You can see that example. And E3 dash will be equal to E3. Why? Because we have rotation about x3 axis, the axis about which we are rotating the system and getting the second system, that will remain fixed. So this is the matrix, transformation matrix between these two set of basis vectors when we are rotating Ei with 30 degree about x3 axis. So you can do this similar questions from your exercise. Go go at the end of this chapter and you will have the exercise and do the questions related with this. Thank you so much. Allah Hafiz.